All right, so I am completely anti-book. For those of you that have me before, you know I give you papers. Okay, I don't pass out a textbook. The reason for that is because when I was like in middle school or something, I popped a vertebrae in my neck. I told you. Did I tell you guys that? No? Okay, so I was in middle school. I wake up one morning. I can't turn my head. My mom takes me to a chiropractor, and the few vertebrae in my neck were not where they were supposed to be. So I had to get a little adjustment done, and it turns out that they got dislodged because I was carrying around a heavy backpack. That weight on your shoulders and moving your neck did something to me. I'm fine now, okay, but it hurt. You know how when you get a stiff neck in the morning? Yeah, it's not the best. So since then, I've been anti-book. For that reason, I'm going to give you paper copies of everything. Are we okay with that? Okay. Does anyone want a book? Because I can give you one if you prefer one. No. Okay. So what I gave you is the first unit that we're going to cover. I think this is a good idea because unlike a textbook, you can actually write on this. Unlike a textbook, you can actually keep this. Okay, you normally turn in a textbook at the end of the school year. You're not going to turn this in. You're eventually going to have a paper textbook of everything we've done this year with every single problem worked out. And I think that's a wonderful resource for you to have if you go into a future math course of some type. Okay, so I really prefer this over a textbook. The first page is your kind of cover page that you can put in your binder so you know it's your math binder if you want to use it. If you go to the next page, that's your table of contents. We're eventually going to fill out all of this. You're going to keep getting more unit papers, but you're just going to keep filing them into your binder. Okay, eventually you're going to build this paper textbook. The next page is kind of the title page of our first unit. We're going to talk about function analysis, okay, getting used to graphs and things. In this title page, it's going to look a little bit different for every unit. The first column is representing how long I think each section is going to take us. This is just my guess. Okay, it might take us longer, it might take us shorter, but this is just my idea. So we'll probably spend today and tomorrow working on this first unit, and then we'll get into the next one on Monday. This is kind of a review unit, just really quick. So today and tomorrow we're going to talk about graphical characteristics, and then we're going to get into everyone's favorite unit circle, right? I see the smiles. The upside down smiles. Okay. All right, so then the next section are the pages in this paper textbook that we're going to be working on for this section. So we're going to be working on pages 7 to 10. Okay? So let's go ahead and start our first section. All right, so given below are different tables of values for different functions. Classify each function by type, sketch a graph, state as many different properties as you can, and possibly find the equation. Okay, lots of information to go through, but I think we're going to be able to do it. So for this number 1, they give us this table, okay, different x values and y values. What do you kind of feel like doing with those different numbers? This is very discussion based. If you just want to shout something out, that's completely okay. Graph them, plot them. All right, so take the time and plot some of those points. They can be kind of tricky because we're working with fractions. Some of the points might be off the graph. You might not be able to plot them, but go ahead and plot as many as you can to try to see what this graph or function might look like.
I lost one.
Pencil? Yeah. Here.
Thank you.
Yep. Can we plot those points? All right. What does your graph kind of look like? What type of function or picture? Can you describe it? If you were to connect the dots somehow, what would it look like? Don't overthink it. A line. There we go. Thank you, Maddie. A line. Do we know what the name is called of a line? What type of function? It literally has a line in it. Linear. Good. All right, so this is a linear function. If you can't read my chicken scratch, you just let me know. Okay, linear. So we classified the type. We sketched a graph. Now we're going to try to identify different characteristics about this line, or maybe lines in general, and then we're even going to try to find the equation of that line. So, what are some things you know about lines? Or even this line specifically? Could be anything. Could go on for, okay, so forever to the, infinitely to the, this is backwards for me. Is this your left? Forever to the left and to the right. Okay, that's what's called a domain. How far left does a graph go? How far right does a graph go? So if this one can go forever to the left and to the right, what phrase or wording would we use to describe the domain? All real numbers. Okay. All real numbers. Does anyone know what the mathematical notation or symbol is that represents all real numbers? Yeah.
It's like an R with two stems.
Two stems, double-stemmed R. Yep, perfect. Okay, so all real numbers, that's a little symbol for it. How can you represent the all real numbers idea using an interval? Like a beginning point, ending point? If you can go forever to the left, forever to the right. Negative infinity to infinity, perfect. And, oh my gosh. Can you help me out with your name again?
Justin.
Justin, thank you, Justin. Okay. All right, domain, all real numbers, forever to the left, forever to the right. What about the range? What do we need to analyze to figure out that idea? Instead of going left and right? Good, Zane?
Up and down.
Up and down. So how far down could this graph go? How far up could that graph go? Yeah. Infinitely. So it's still all real numbers, double-stemmed R, in negative infinity, positive infinity, same idea. Do you think that this domain and range is just for this line that we drew, or all lines that exist? If I were to draw a different line up here, does it still go forever to the left and right? Still forever down and up? Yeah, okay. So domain and range for all lines are all real numbers. Perfect. All right, what else do we know about lines? Anything whatsoever. Zane? Were you stretching or did you have your hand up?
I have no idea.
You have no idea? It was a combo of the two of them? Okay. Do we know any equations of lines? That's been burned into your brain since middle school probably. Y equals mx plus b. Do we remember the name of that form of line? We're whispering it. I can hear it. JC? Say it again. Slope. Close. Slope. Intercept. Thank you. All right. Slope. Intercept. All right. Now, since it's called slope-intercept form, we must be able to find the slope and the intercept based off of that equation. So, what do you think the B represents and what do you think the M represents? which one of those is the slope, which one of those is the intercept. Good, Zane?
B is the y-intercept.
Y-intercept, perfect.
M is the slope.
M is the slope. Okay. So, can we, based off of this graph that we have, identify either of those ideas? Can we find the slope of that line? Can we find the y-intercept of that line? Go ahead, David. Which one do you want to do?
Well, the y-intercept is -3.
Perfect.
0,
0, -3. Okay, so you can see that based off the table. Good. But you can also see that based off the graph. Wonderful. What about the slope? We have options. Perfect. Okay, now when you have a table, you can pick two really easy points to work with. Probably not the fraction ones, okay? But if you can pick two easy points, how can you use those 2 points to help you find the slope? Do we remember the little formula or method to do that, good, Zane?
It's like y2 minus y1 over x2 minus x1.
All right, it's not like that. It is that. Perfect. Okay, so you can choose 2 points based off the table to help you. Maddie, you also said you could count. What do you mean by that?
You can do like rise over run.
Okay, based off the graph, we can do rise over run. So pick 2 really good points, like the ones that go in between the crosshairs or tick marks of your graph, and we want to calculate the rise over the run. So to go from one point to the other, it looks like we have to go down 2, but to the right 3. So what would the slope be? Down 2, right 3. Good, Zane? -2/3. Okay. So if we can identify those 2 different pieces, that must mean we can figure out the equation of this line. Notice how they identified this particular equation as capital F of x. So we're going to say capital F of x equals, we have mx plus b, but we know the m is -2/3 and the b is -3. So there's the equation of your line. Perfect. Anything else we know about lines? Anything else about a linear function? Let's see, slope-intercept is one way to represent a line. Do you know a different form we could possibly use? There's actually 2 different ones that we're going to talk about. Go, David.
There's 1 point slope form.
Yeah. Do you know it?
No.
It's okay. This one is actually kind of the less common of the 3, but you're going to learn to love it this year. We're going to use it all the time. You're going to learn to love it. Point slope. Does anyone know it? Kind of? What's in it? Braden, you want to help him out?
Y minus y1 equals this m times the quantity of x minus x.
Perfect. We used that a lot last year, right?
Oh yeah.
Oh yeah. All the time. Point slope form. It's going to be your new best friend. Okay? So the m still represents the slope. Thank you. And in this case, the x1 and y1 are coming from a point, okay, an ordered pair. The third equation format is called standard form. This one's a little different. It's like ax plus by equals c. Does that look familiar? Yeah? Okay, a, b, and c are normally whole numbers to work with, so that's nice. But that's another way a line might be written. Anything else about lines? I think that's pretty good. We're just going to write down one more. Okay? If you were to pick these 2 points, we know the slope is -2/3. What if I were to pick a different pair? For instance, those 2. What's the slope between those 2 points? It's still -2/3. What if I were to pick a different set? It's still -2/3, okay? So what's interesting about a line is that they have what's called a constant slope. Rise over run, over and over and over and over again. It never changes. Okay, it's a constant slope. And this constant slope is actually what's causing you to have a straight line, because it's the same all the way through. We're eventually going to see, well, what if we don't have a constant slope? What does that do to the graph? Okay? How are we doing with lines?
Please excuse interruption. I need following students report to the office. Anna Greco, Amanda and Emily Huff, Mackenzie Jack, Maura Penn, Grayson Schwager, Riley Troutman, Jameson Hill, Brandy Scott, and Vanessa Ward. Thank you.
All right. Let's go ahead and try the next one. What do you feel like doing? Can we plot some more points? Go ahead and do it. So if you were to play connect the dots, what type of function might this represent? Good, Zane?
Parabola.
Very close. Okay, so what does a parabola look like? It's a U shape. Okay, so a parabola is a U shape. Does this resemble a U or another similar letter? Yeah. An absolute value. Okay, this is a V. Very close. Okay, absolute value. Now, the reason it's a V instead of a U is because notice how we have that constant slope. You see how it's a line all the way through? Okay, it's not curved like a U. You have that constant slope. So this is an absolute value. All right. So what are some things we can list down about an absolute value graph? You want to go through domain and range like we did with a line? What's the domain of this absolute value graph? How far left can it go? How far right can it go? Good, Zane? Infinitely. So we have that all real numbers idea. What about the range? How far low can it go? How far high can it go? This one's a little different. It's not all real numbers because we don't have any graph towards the bottom. -3 is the lowest point, and then what's the highest point? Infinity. Okay, so in terms of like the parentheses and brackets, hopefully we remember the difference between the two. Okay, where can we put a parenthesis? Where can we put a bracket? Why? Perfect.
Because you can touch -3.
You can touch -3 and you can never touch infinity. You're just going to go on forever. Perfect. So my question to you is this domain and range the exact same for every absolute value function, or does it change? What changes?
What you can touch and what you can't.
What you touch and what you can't. Perfect. So just for instance, if I were to draw another absolute value, would the domain still be all real numbers? Does it go forever to the left, forever to the right? Yes. So this domain is all real numbers. That will never change. But what's the range? In this case, it might be -7, right, instead of -3. So the domain's not going to change, but the range will, depending on where your absolute value is located. Okay, so it's a little bit different from a line, because for the line, the domain and range was same for every line, but not the case for absolute values. All right, let's go ahead and see if we can figure out the equation of this absolute value. So this one's labeled g of x, and since it's an absolute value, we're going to need those absolute value bars. We know there's going to be an x in our equation somewhere. So this is when we're going to dig deep, okay, into our brains. Typically, an absolute value starts at the origin, okay, that middle point. but notice how this one has its vertex or beginning point here. How was it moved? Can you describe how it was shifted? If it originally started at the origin? Left 2, down 3. How does that transformation show up in an equation? Any guesses?
Isn't the up and down on the outside?
Yep. Down 3. Good. We're digging deep. What about left 2? Yeah. Say it again. Right here? That's kind of our slope. We're going to get to that in a second. After the x. All right, so how do I represent left 2? Plus. It's the opposite of what you would think. Yes, perfect. Okay. Now, Jarrett brought up a good idea here. We may need a number out front, okay, because maybe the slope has changed. Okay, maybe we stretched it a little bit. What is the slope of this absolute value? Maybe you can count the rise over run that I kind of dotted in earlier. 2. All right, positive or negative? Why positive? Good. Okay, notice how the V shape opens up. Okay, a positive direction, so that is a positive slope. Even though this line has a slope of -2, okay, the entire graph is positive because it opens up. Perfect. Wonderful, wonderful. Do we remember that from last year? Those transformations? At least if we went over it right now a little bit. All right. Let's see. Do you think we have constant slopes in this absolute value? Is this slope the same as this one? Yeah? What about this slope compared to that one? Are those the same? Do you go up and over the same amount each time? Yeah. So we have a constant slope on this side and a constant slope on this side, but aren't they opposites? Isn't this one a negative slope versus this one's a positive? Do you see that? Okay, so we do have that constant slope because an absolute value is comprised of straight lines, but they are opposites. We'll say for each leg. So if you notice, the slope on the left leg is -2, whereas the slope on the right leg is +2. They're constant, but they're opposites. Doing okay? Anything else about absolute values you guys want to add? No? Okay, that's good for me. Let's take a look at the back one. Go ahead and plot some points. Anybody have grease for that fan? Because I'm ready to throw it out the window. It'll come in handy around Halloween time, right? That squeaky door. All right, what type of function do we have? Or shape? Now it's a parabola. Good. Do you see the difference between the U shape and the V shape? U is more curved. Okay, if that's a parabola, what's the name of the function? The quadratic. Good. All right, quadratic. So let's go ahead and list some things that we know about quadratics or parabolas. Maybe we'll start with the domain and range again. What's the domain of this parabola? How far left, how far right? Remember, these arrows mean it's just going to continue forever. All real numbers. It's going to go forever to the left, forever to the right. What about the range? Low to high? Negative infinity to 4 with a bracket. Perfect. Do you think that's the domain and range for all parabolas? I mean, that's correct for this one, but do you think that's the same for all of them? No, definitely not. Because if I were to draw another one, the domain would still be all real numbers, okay, forever to the right and forever to the left. But notice how the range in this case would be 5 to infinity. Okay, that definitely changed. So the domain stayed the same, but the range happens to be a little bit different. Okay? What about the slopes? Do we have constant slopes in a parabola? If you pick 2 points, there's a slope. If you pick 2 points, there's another slope. Are those the same slope? No. Okay, so in this case we have various slopes. So when the slope changes, that's actually what causes your graph to bend. You get some type of curve to it. Okay, so it's not constant. It's no longer a line. We have some type of curvature to it. Perfect. Various slopes. Let's go ahead and try to find the equation. This time we're dealing with h of x as the name. So if this is a parabola or a quadratic, we're going to have a quantity squared and an x in there somewhere. Just like the absolute value, a quadratic normally starts at the origin, but notice how this one has moved. Okay, its vertex is kind of at the top right there. Can we describe the transformations? How did it move?
Right one up 4.
Right one up 4. So how would those show up in our equation? Right one up 4.
Plus 1 on the outside. And minus 4 on the inside.
I think you got them switched.
Oh,
Okay, plus 4 is up 4, and then right 1. Do we need a number or something out front? Go, Jarrett, you're shaking your head? Yeah.
It's a reflection.
It's a reflection, so what do we need?
Negative.
A negative, it flipped. Perfect. All right. We doing okay so far? All right, we're going to finish up the quadratic tomorrow and we'll work on some more graphs.